My name's Dan Suri. I'm a principal operational meteorologist at the Met Office and also work in the O2R space at the Met Office. So on shift, I'm basically the lead or the chief forecaster, and I'm responsible for producing overarching guidance on the forecast to ensure the Met Office have a consistent story. I'm also responsible on shift for issuing public service warnings, which we're going to talk about in this presentation. And there's also a leadership and incident management component when I'm on shift as well, whereby I'm responsible for the smooth running of the shift and team well-being and such like. And then off shift, which is basically I have a 50-50 function, 50% of the time on shift, 50% of the time I'm off shift. And then I work in the operations to research space at the Met Office, where my responsibility is to represent the operational community to groups and processes that need an operational perspective. And that's to help that things like new models and tools do what the operational community need them to do, and so on and so forth. Okie dokie. So, oops. So the outline of this presentation then, we're going to talk about the National Severe Weather Warning Service. That's one of the Met Office's key outputs. I'll explain what this service is, I'll explain how the warnings are made, and this will include some discussion about some of the tools used to make these warnings. And then with me today, I've got Met Office Senior Scientist Rob Neal, and Rob, will go over to Rob about halfway through my presentation to allow Rob to talk about one of the decision aids that he's made and developed to help make these warnings. And then we'll finish off by talking about the climatology of our warnings and the role of the Met Office civil contingency advisors, who are key in communicating these warnings. I'll just turn my pointer on because I'm going to need this shortly. And then, so first of all then, what is the National Severe Weather Warning Service? Well, first of all, we call it NUSWAS. That's the sort of acronym we use for it. And yeah, NUSWAS is the UK's public weather warning service. It's something that we're funded to do at the Met Office by the UK government, and it's aimed at a number of different sectors. It's aimed at the general public, businesses, emergent responders, and government. So basically, it's a catch-all public warning service aimed at everyone. And what we find is that NUSWAS warnings are a very, very effective way to tell a large group of people about impactful weather in the forecast. And the way that NUSWAS warnings work is that they are an impact-based service, warning about the impacts of severe weather. And this is important because it's not a threshold-based service, it's an impact-based service. And we'll talk about what sort of impacts we're thinking about as we go through the presentation. But that is an important element of it. We warn for 8 elements, and we use an impact matrix to help communicate the warnings to people. So a brief history of the service then. So in October 1987, there was a really big storm over parts of the UK, particularly affecting southeastern England, some very high winds, and it's an extremely disruptive event. That's known in the UK as the Great Storm of October in 1987. Since then, as a result of that storm, NUSWAS was set up, and since then it's evolved into an impact-based warning service offering multi-hazard warnings up to 7 days ahead. Now, the 1987 storm resulted in 18 deaths, widespread damage to buildings, hundreds of thousands of homes left without power, millions of trees were uprooted or damaged. It came in a period where it had already been very wet, so that no doubt helped exacerbate damage to trees. But one of the issues was that it was a very difficult forecast to make because the depression that brought the high winds, the track of it was very, very finely balanced as to whether it would track along the English Channel or whether it would actually pull into the UK and therefore take its swathe of high winds with it into the UK. Now, at the time, ways of communicating to emergency responders and the public and such like that severe weather was likely to affect the UK were quite limited. The main way was via TV and radio broadcasts, but this was a little bit unreliable, it wouldn't reach everyone and so on. And the last TV weather broadcasts that were live were mid-evening at the time as well. So, you know, a big change in story to a much more severe event happening in the mid to late evening, it was difficult to get that kind of message out there. Now, as I say, the track of the storm was quite uncertain and quite complex, and the forecast changed to capture the track a little bit too late, really, to catch the mid-evening broadcast. So people weren't as well warned as they perhaps otherwise would have been had there been other mechanisms in place to get warnings out. I'm just showing a couple of weather charts from the storm. So what you can see is these are our analyses. These are in black and white, and I appreciate they're perhaps a little bit difficult to see. This is at midnight UTC on the 16th of October, and this is 6Z. And so what you can see is the storm just getting towards the southwest of England at 16 UTC, and then by at midnight UTC, and then by 6Z in the morning, it had pulled away to be just east of England into the North Sea. So basically, the track had taken it. This dotted line here is the track actually. So the track took it from just to the west of northwest France, across central parts of southern England, and then away towards parts of eastern England. These are the maximum gusts from the storm over the UK. So you can see these are in knots. So you can see that on the south coast of England, we had gusts in excess of 90 knots at several sites, and then even inland there were some exceptionally high gusts, gusts into the 70s and 80s of knots in places in parts of southeastern England and also eastern England. I mean, that's really quite exceptional. So you can see that was really quite an exceptional storm with some really high winds. At the time, I was living up here in northeastern England, and you can see the gusts were much lower there. So what I particularly remember of the storm is waking up in the morning of the storm, putting on the TV to watch a bit of breakfast television before going to school, and there wasn't any telly because the power had been knocked out by the storms and television stations were down and stuff. I believe these slides will be made available later on for people. More details about the storm from an infographic that the Met Office put together, just saying a little bit more about some of the damage and some of the stats about the storm. But one of the headline messages is that for the UK, this was considered the most damaging storm since 1703. So a really major event. And unsurprisingly, there was a lot of inquiries and such like in the aftermath to explore how the storm could have been better forecast and how the risks and hazards associated with it all could have been communicated differently. So, as a result of the storm, there was a government inquiry, there was some discussion about what the Met Office could do differently, and it was decided to set up the National Severe Weather Warning Service, NSWS, and that went live in 1988 as a threshold-based warning system. And it stayed like that for a good few years. And then in the mid-2000s, we started to see some developments and evolution of the service. So in 2007, we had some serious summer flooding across large parts of the UK. And that led to the creation of a combined Met Office and a combined Met Office and Environment Agency hydrometeorological unit to provide a continuous process of forecasting rainfall from the Met Office, forecasting the rainfall to the Environment Agency, forecasting flooding. And that's been a really successful move. What's happened is Met Office forecasters have trained as hydrologists, Environment Agency hydrologists have trained up as meteorologists, and we have this team of hydrometeorologists. The Met Office obviously look after the weather in the UK. The Environment Agency are responsible for elements of river management and flooding. Then in 2011, we changed from a threshold-based service to a impact-based warning service, and that's because what we were finding was that the threshold-based approach doesn't take into account other factors that could be key in impacts of weather, such as time of day and year. You can imagine that a major windstorm happening in the middle of the night is going to impact people in a very different way to how it would impact people in the middle of the day. And then, of course, there's variations in sensitivities to weather which vary across the UK. So, for example, one of the old thresholds was 15 millimetres of rain in 3 hours, which in some parts of the UK could be problematical. But for some parts of the UK, that's very normal and therefore not a particularly good threshold. Antecedent conditions are, of course, important as well. Obviously, if it's been very wet for a period, then clearly you need less rain to get impacts, and so on and so forth. So in 2011, we moved from a threshold-based warnings approach to an impact-based warning system, and we also introduced a matrix, which I'm sure many of you are familiar with, given the number of other organisations and services that use similar matrices. But this matrix is a probabilistic matrix to try and illustrate and indicate the likelihood of weather conditions reaching certain impact levels as well. Then in 2015, we set up a storm naming collaboration with Met Erin, which was introduced to complement NSWS warnings. That focuses mainly on windstorms, but if a storm is going to give a lot of other major impacts and there is a wind element, then the storm will be named as well. In 2018, the lead time of our NSWS warnings increased from 5 days to 7 days, and we added some new warning elements. The Cairn and me joined the storm naming collaboration in 2019, which was great and makes an awful lot of sense given that a certain amount of Dutch weather is effectively second-hand British weather. And then in 2021, extreme heat was added to our warning categories as well. So what elements do we warn for then? there's a number of different categories there: rain warnings, fog, ice, snow, wind, extreme heat, lightning, and thunderstorm are the warning categories that we have. It may seem slightly strange seeing thunderstorm and lightning as discrete entities, and by thunderstorms, what we're thinking of is that they're warnings that we tend to use more in the summer half of the year when we're considering a full gauntlet of convective hazards. So a thunderstorm warning would include lightning, high winds potentially, hail potentially, and also rain, noting that from UK convective events, rain and flash flooding tend to be the main hazards. The lightning warnings are actually more used in the winter time, when we have situations where we have a convective event which will be over pretty quickly but could generate quite a lot of lightning, but very little in the way of other convective hazards. So it's to try and make a bit of a distinction between types of convective warning, I suppose. So the impact matrix then. So the way our impact matrix work is that we plot likelihood and impact onto a matrix, which we then use to help communicate warnings. Plotting the likelihood against the impact allocates the warning a color, and the location of the tick in the box, as we're going to see shortly, is very, very important, not the color of the warning. So when we issue our warnings, we encourage users to actually go and look into it, read the warning, and understand where the tick in the box is, because clearly, for example, a yellow warning could mean some quite different things. A yellow warning could mean a very low likelihood of a high impact weather event, which obviously could mean severe weather is possible, but very low likelihood. But conversely, a low impact, a yellow warning could also mean a low impact warning. That's a high or medium likelihood, which is just basically the weather being a little bit worse than normal. So there's quite a lot of information that we have contained within our warnings. So here we've got a typical NUSWAS warning. Yeah, I appreciate this slide perhaps looks a little bit messy, but I've sort of broken it down to try and highlight the main areas of what's within the warning. So what we've got is we've got the main headline, which includes the headline message, the validity time, and the color of the warning and element. We then have a map showing the warning area, and then we talk about expected impacts. Now these aren't every single impact. We can't cover in a warning space every single possible impact, but what we do is in our what to expect statements are give a flavor of what are considered to be some of the main sorts of impacts that we could expect from the weather event on offer. We then have a section about further details where we will say a little bit more about the weather event. So in here we will perhaps give some figures about how much rainfall is expected, or magnitude of wind, or depth of snow. We might say a little bit about how the weather event is going to manifest itself. So, Storm Kieran moving across the UK, bringing with it a lot of rain and wind, something like that. And we'll also then talk perhaps a little bit about some of the uncertainties there. So, for example, there's a sentence here saying that these higher totals now seem more likely to the south of the warning area, roughly to the south of the line, Glasgow to Edinburgh. So there we're trying to give a steer to try and help people using the warning understand how the warning has evolved and which bits are where the weather's likely to be worst in that warning area. And we might say something about the timing as well. It might be that, within a given warning area, the worst impacts will start off in one part of the region and then transfer to another part of the region later on. So we might say something about that. Issue time and update time are indicated there, and we also have where we are on the impact matrix indicated. We do mention why we've updated a warning as well, in case people want to know why that is. Sometimes we'll extend or trim a warning area, so it's useful to get that information across to some people. And then something we've introduced quite recently, within the last few months, in fact, what we call what to do statements. It's one thing telling people what to expect, but obviously people need to know what to do about it, really. So we've worked quite hard to come up. We've done some external research and used an external research company to come in and help us and work with us to understand what are appropriate kind of what to do statements to suggest to people, so that people have got some ideas of things they can do. So in this case, this is a rainfall warning, so we're talking about things that they can do to prepare for flooding, such as have torches and batteries and a mobile phone power pack, that kind of thing. But it might also be, in the case of a wind warning, it might be things like suggesting that people tie down loose objects in their garden, that kind of thing. So we're making a number of these kind of statements to really help people understand what it is they can do to change their behaviours around a weather event to minimise the chances of impacts. Now, when it comes to working out what the impacts of an event could be, we have a few guidelines to help us here. What we've done is we worked with the emergency responder community to get a sense of what sort of impacts weather events could generate, and whether they would consider them to be a high impact, a medium impact, or a low impact. And that provides us a bit of a guide, and it allows us to shape what sort of impacts we think could be associated with different kinds of weather events. Now, what we see here are very general impact and advice statements that apply to all severe weather. We do have some more specific statements for each individual weather event, each individual weather element that we warn for, and there's more information about that on our website. And before we finish today in the Teams chat, I'll post some links which will both include some additional information about our warnings, but it will also include some links to some papers about some of the tools that I'll come on to talk about shortly. So we use these impact statements, or these impact tables rather, to try and help us decide where we're going to be on the impact matrix. So if we think that the kind of weather on offer is going to give us some impact journey travel times, then if it's going to be a long time, then we'll be more in the medium and high impact column, and if not in the low impact column. If we think there could be danger to life from injuries and flying debris and that kind of thing, then obviously that's more of a medium or high impact as opposed to a low impact. But a sort of simple rule of thumb way to think about this is that responders should be able to cope with low impact warnings, and there should be limited inconvenience to the general public. So a low impact warning would say, it would be basically saying the weather's worse than normal, you need to have a bit of a think about what you're doing, but it shouldn't be anything out of the ordinary. A high impact warning, on the other hand, it would be an event where there's longer term strain on responders, and the public would be greatly inconvenienced and really need to change behaviours. For example, travel, public transport won't be running very well, if at all, so journeys won't be able to be made, and you'd be better off working from home on those days, that kind of thing. So another way of thinking about this then is, and this is where it's important to understand where the tick in the box is on the impact matrix, is to have a bit of a think about what low, medium and high impact warnings mean. So when we have a low impact warning, what we're saying is some short-lived disruption to routines, business as usual response from emergency services, some impacts on travel, maybe some slightly longer travel times. But then when we think about high impact event, what we're talking then is some really much more prolonged disruption to travel, long delays, potential for people to be stranded for long periods of time, potential for cancellations, and of course also we have things like danger to life and extensive damage to property and buildings being potential impacts from a high impact event, prolonged disruption to routines, prolonged strain on emergency responders, that kind of thing. So you get a sense that a low, the differences between a low and high impact event there. And of course, because of the way the matrix works, and this is where it's really important to look at that, you have yellow warnings that can be these high impact events, but they can also be these low impact events. So we really strongly encourage people to look where they are, where they're ticking the boxes on the matrix, to understand both something about how the event could manifest itself in terms of impacts, but also about the likelihood of an event. Clearly, if you're in this column, if you're in this box here, well, there's a good chance that the event may not actually happen. Or there's not enough confidence at that point to be any higher in the box. This box we'd perhaps more tend to use at longer lead times when there's a lot of uncertainty about an event, but we're saying, well, look, this could be a bad event. We'll have more information when we have more confidence in how the event will manifest itself, and then it may be we then move up the column here because our confidence in a high impact event is increasing, because model uncertainty is resolving itself and we can see clearer signs that it's definitely going to happen. Or it might be that the models change a little bit and we drop from this box into this column, or even this column, probably more like this column really. But yeah, during the course of an event where you are on the matrix can evolve. Okay, so that's a bit of background then about the NUSWERS warnings, what they look like and what they show. We'll talk now a little bit about making a NUSWERS warning, and then I'll show you some of the tools we use. So we're probably about 5 minutes away from going over to Rob for him to talk through one of the key tools that we use that he's developed. So the way that making a NUSWERS warning works is it's a collaborative approach. We have a team of operational meteorologists at the Met Office called the Expert Weather Hub. That's the team in which I work, and the Expert Weather Hub are responsible for issuing NUSWERS warnings, with the duty chief operational meteorologist having the final say. So that's the role I fill when I'm on shift. Warnings can be issued at any time, but the majority of warnings are issued during the working day, during the morning, and that's because we know that if we push out our warnings during the morning, that captures maximum reach. We make all the daytime broadcast cycles. People in businesses and organisations who take these warnings, they're obviously going to be at work, so they're going to be in a position to receive these warnings, and general public are obviously going to be awake, so they're going to be more able to receive these warnings as well. Warnings are based on the potential for impacts from weather rather than a threshold meteorological value. That said, we do know that impacts can be underpinned by a threshold, but the thing is, thresholds can't always be usefully or consistently defined. So you could think of the amount of wind to blow over a tree, for example. If the ground's wet and saturated, a tree, and the tree's in leaf, it's going to blow over a lot more easily than if the tree is in slightly dry conditions and not in leaf. So yeah. We do think in terms of some nominal thresholds at times. There's a lot of forecaster experience comes into making these warnings as well, but fundamentally it's all about the impacts. Producing those warnings is a collaborative effort. The expert weather hope focus on the meteorology of the event, so we get a picture of the synoptic situation in our minds, understand what the sort of magnitude of weather hazards could be, how much rain could fall, how high will the winds would be, how much snow, how likely is it for thunderstorms to develop. We then have a group of people called the Met Office Civil Contingency Advisors, MOACs, we call them for short, and I'll talk a little bit about them more specifically later on in this presentation. But what they're doing is they're providing situational awareness of sensitivities and potential impacts via liaison with responder and government community. So what they're doing is they're working with the emergency responder community, working with local and national government to understand what the sensitivities are, what the potential impacts could be of an event, and that obviously feeds into the NSWS warnings. Other forecasting teams, especially the hydrometeorological community, work with us to give us some information regarding sensitivities, and likewise some stakeholders do as well. So we work with the hydrological community to understand what rainfall can do. We work with the health specialists when it comes to extreme heat warnings to understand what the potential impact and magnitude of heat could be. So we're working with a lot of different groups then to get these warnings together, and then we have internal communication teams to help us communicate these warnings. We have a press office, obviously, who are responsible for a lot of our content that goes out to the wider world. We have a team of forecasters called the Media Services team, and what they do is they're providing briefings to television stations, radio stations, and also providing some content on social media around and helping and producing some of the video content that you see on our website. So that's all out there helping communicate the warnings. And we have a public-facing phone and email area where people can message in and contact the Met Office, and they call the weather desk, and they're able to provide some of this advice about the warnings as well. So making warnings a collaborative process. That makes it sound like a little bit of a cumbersome process, perhaps, but I don't think it is. I think it's really a necessary way of doing it, that we do need to build up a picture of what all the impacts can be and how an event will manifest itself. And so you need, a team of forecasters focusing on the meteorology of the event, thinking about the likelihood of the event coming off, and then understanding the impacts. Well, that's where a lot of other people come into it all, and from there we come up with the warning. Okay, moving on to the tools then that we use to make these warnings. There's a wide range of tools, as with any meteorological organisation. There's a wide range of tools we use to look at these things. We have access to a broad range of deterministic and ensemble outputs at the Met Office, both from our own modelling suite and also from other centres, in particular ECMWF. Models that we use from our own modelling suite are UKV, which is our convection permitting high resolution model, our global model, the GM, and then we have MOGREPS G, which is our global ensemble model, and we have MOGREPS UK, which is our convection permitting ensemble. We use those outputs alongside some post-processed ensemble output called Improver. And then alongside these general outputs, we also like to use EPSW, which Rob's going to talk about shortly. That's a decision aid which takes model information and gives an indication of where an event could be on the impact matrix. There's a number of ECMWF outputs that we find pretty useful. EFI, the Extreme Forecast Index, is really useful for some sort of contextualization against climate, in this case a model climate, of course, but we find that a really useful tool. Dalmatian plots, I'm sure many of you are familiar with them from the cyclone database at ECMWF's website. That's really useful to assess cyclone tracks and intensity. EPSW, well, I've just said a little bit about that, but that really is a useful tool helping us decide where an impact matrix or warning should lie. And then we have some more specific impact models that have been developed to help us home in on certain types of hazards. So the vehicle overturning model and surface water flooding hazard impact model obviously speaks for themselves what they're looking at, but they provide us with some really useful information. And we have some feature specific tools such as a proxy for sting jet potential, which can obviously help us as well. So this is my penultimate. This is the last slide I'll show before we go over to Rob. But this is a little bit of a summary of the Met Office's current model suite. So the UK NWP domain, you can see, extends from southwestern Scandinavia across much of France and then out to the area west of the UK. We have a 1.5 kilometre resolution deterministic and 2.2 kilometre ensemble model there with 70 vertical levels, and that goes out. It runs hourly. Most of the time it's 12 hours, but every now and again it goes out a little bit further. Some runs go out to 54 hours, and a couple go out to T plus 120, and the global model, our global model is a 10 kilometre model with our ensemble at 20 kilometre horizontal resolution, 70 vertical levels, and they go out in 6 hourly steps to either T plus 54 for the 6Z and 18Z runs, and the main synoptic hour runs, the midnight and 12Z runs, go out quite a lot further. So that's a bit of an introduction to NUSWERs, and then what we'll do now is we'll go over to Rob to talk about EPSW, and then when Rob's finished, we'll come back to me. I'll talk about some more of the tools that we use, and then talk about one or two other things as well. So I'll hand over to you now, Rob, if that's all right, please.
Yeah, thanks, Dan. Okay, hi everyone. My name's Rob Neal, and I'm a scientist at the Met Office. So I work really closely with the forecasters, people like Dan and others. Really, I'm working as a post-processing scientist, working predominantly with ensemble data, trying to create forecast products and tools that will help the operational meteorologists sort of get the best out of the ensemble, because here's a postage stamp example here. Clearly the ensemble is providing masses of information, sometimes or quite often too much information. The forecasters just don't have the time to delve into it fully when they're on shift, and so my role working with others is to try and synthesize this information and to try and draw out the key signals from it. And this is particularly important when we're trying to identify probabilities for high impact weather, which will often be quite low probabilities. So one of the tools I've developed is an ensemble prediction system first guess warning tool, specifically to support the National Severe Weather Warning Service. And I thought it'd be nice to start by going back to the Great Storm of 1987, which Dan started off by talking about, because following this, the Met Office started issuing warnings, and it's probably fair to say it wasn't a well forecast event. But we've been able to rerun the ensembles now using old initial conditions, using global reanalysis. So here's an example that Tim Palmer produced. Some of you may know him. This is from when he worked at ECMWF, and he reran their 51-member ensemble for a date in October 1987 using initial conditions from the global reanalysis. And what we have is we've got the analysis here showing the Great Storm, and you can see it tracks relatively far north with strong winds across southern England. And then here's the control member forecast. And if we just had the control forecast, essentially treating it as a deterministic, like we did in 87, then you can see the stronger winds are going over France, and it's a weaker low. But because we've got 50 perturbed members as well to add on to this, we can then see, look, we've got maybe 10 to 20% of the members now do have a very deep low. This is a 2.5 day lead time. So imagine if we had NUSWERs and this ensemble back in 1987. It's quite interesting to start to think about where in the matrix we might have issued a warning. Clearly there's a potential for high impacts here. So the chances are we would have issued a yellow warning, maybe in the high impact column, which could then be escalated to amber and maybe even red at shorter lead times. So one of the tools that I produce is called EPSW, which stands for Ensemble Prediction System First Guess Warnings. And it tries to mirror the National Severe Weather Warning Service. So it uses the same color scheme, the same warning levels, the same weather impact matrix. As Dan mentioned, it's a decision aid tool for the operational meteorologists to support NUSWERs. It's based on a combination of likelihood and impact. So what it does is it creates probability maps for low, medium, and high impact weather using a set of predefined sort of proxy thresholds for those impacts. and then it has an algorithm which aggregates them all together to produce an overall warning color. And it, as well as providing an overall warning color, it also provides an estimate for where within the matrix the warning should be issued. And it's really just it's a first guess tool. This never goes directly out to the public or the responders. It's a tool that's only seen internally at the Met Office by the operational meteorologists. So yeah, it uses a set of varying thresholds. And by that I mean thresholds that can vary spatially. For example, for wind thresholds, we might have lower thresholds in southeast England compared to, say, up in Scotland, where they're more used to strong winds. And the thresholds can also vary throughout the year. So again, for wind, keeping with wind, we use lower thresholds in summer because obviously trees are in leaf and maybe more people are camping, doing outside activities. The first guess warnings are presented in map form, and increasingly we're using output from Improver, which is our ensemble post-processing system, which brings together ensemble information from all the ensembles that we use in the Met Office. And here's an example of what EPSW looks like in sort of graphical form. This is what the forecasters see. This is an old example, but it illustrates the point. It's from Storm Doris in 2017. And what the forecasters see, well, first of all, they're presented with this overall warning color map. And then they have the option then to drill down and look at probabilities for low, medium, and high impact weather. So here's the probability for low impact, medium, and high. And you can see that the color scale here is all yellow for low impact. So anything above 50% is colored in yellow, and then that corresponds to this column within the matrix here. So you can see here we've got dark yellow shading, so that would mean this position within the matrix. But the algorithm is designed so that impact takes priority over likelihood, because it's generally better to warn for a low probability of a high impact event than a high probability for a low impact event, because at least then you're giving people a chance to prepare for the worst case scenario. So in this case, we've got quite a large area here with medium impact probabilities, with high and medium impact probabilities above 80%. So that would suggest a tick here within the matrix. And there are some areas showing a high probability of high impacts, but that it's covering relatively small areas of the UK, and they're areas that are not highly populated, maybe where there's not much critical infrastructure, perhaps. So anyway, so overall, a good suggestion might be to put the tick here in the matrix, as a high probability of medium impacts. And of course, this is the first guess, and then the forecasters working with the regional civil contingency advisors can then obviously tweak things based on how they see things at the time, and also from looking at other output as well. And that's what the forecasters ended up issuing. So an amber warning over a similar area to the first guess warning, but they just put the tick one box lower within the matrix. And then just two more recent examples. So Storm Eunice in February 2022. This was a big event for us in the UK because we had two very rare red warnings issued, one for southwest England and one for southeast England. And you can see the low there at midday on the 18th of February. This was a Friday. It's a normal working day, and the storm was forecast to come through during normal working hours. So potential for big impacts as people are out and about, going to school, going to work, and so forth. And in this panel here, we've got the forecaster issued warnings. So the first yellow warning was issued at a 4-day lead time, covering a very large area, which coincided with the storm being named. And there was the tick in the matrix, a low probability of high impacts. Then it was escalated to amber, again keeping within the high impact column at a 2-day lead time. And then finally, within a 0 and 1-day lead time, we had these two red warnings embedded within the larger amber warning. And then here, to go alongside that, is the evolution of the first guess warnings from EPSW. So EPSW first started flagging stuff up at a 6-day lead time, but of course the warnings were in completely the wrong area. And then the next day, the warning sort of area shifted south but forecasters still didn't issue a warning, I guess because they were still waiting for the models to sort of settle down and stop jumping around. So it wasn't really until a 4-day lead time that the first warning was issued. I think this follows 2 days in a row of the models sort of being consistent in where they thought the highest risk areas were. And then you can see we've got amber and even areas of red flagging up at a 1-day lead time from the first guess system. So yeah, really good consistency from a 5-day lead time, which led forecasters to issue their first warning at a 4-day lead time. And then just one more example, Storm Kieran from November 2023. Here's Storm Kieran, sort of similar storm to Eunice really, but actually it was much deeper. So I think it broke some new records for the depth of the low, central depth. Here we've got 953 millibars. And just to compare that again to the Great Storm of 1987, that was again quite a similar storm. In fact, it was deeper than the Great Storm of 1987. And then here's the evolution of the first guess warnings. This is using improver output, our sort of blended ensemble output. So Storm Kieran affected the parts of southern England over 2 days, sort of overnight on the 1st of November and into the early hours of the 2nd of November last year. And there was a lot of uncertainty here. So at a 4-day lead time, we've got this sort of fairly large yellow area with the amber across just the south coast. But as the lead time reduced, the ensemble was sort of, most members were tracking further and further south. So it was trending south over time. So this did provide a big challenge to forecasters, because obviously they'd issued a yellow warning early on, and then they had to sort of pull it back a bit as the lead time got less. But then these are probabilistic forecasts, so I think that's it's going to happen from time to time. And then this is what was actually issued. So we can see a sort of a wide yellow area with an embedded amber within that, both within the high impact column. So yeah, just as I draw my section to an end, before I hand over to Dan, I just thought it's worth flagging up this diagram of the warning value chain, because I just want to make the point that this EPSW tool is just one cog essentially within the much wider chain of products, tools, and capabilities that are involved in producing a warning and communicating that warning. So EPSW is really adding value in this part of the chain. It's taking information from the weather forecast and identifying the main hazards, flagging those hazards to the forecasters, who then turn those into impacts through chatting with the regional civil contingency advisors who work for the Met Office. And as Dan will say, they have links to the responder community in different regions of the UK. So then Dan will produce the warning after interpreting all this information, and then the end users, whether that's the public or the responder community, will make a decision based on that warning. So I'll end that there and hand back to Dan to finish off. Thanks, Dan.
Great, thanks, Rob. Yeah, that's really, really interesting and a really great talk, Rob. The tools, Rob and I have worked together for a long time, and Rob's developed a number of tools that help the Met Office operational community. And the work that Rob does is really, really good. He's come with some really, really good tools and some great stuff. So yeah, that's fantastic, Rob. There's 2 or 3 questions for you in the chat, and at the end of the chat, I will post. I'll post a link to your paper about EPSW as well as some links to some other papers as well. Okay, so I shall move on then to show you a little bit about some more of the tools that we used. And it was interesting to see the example of Storm Kieran there, by the way. That was really, really difficult, actually. I was on shift for part of the build-up and part of the event. And one of the things that was really, really challenging is just the notion that you could have had really, really high winds impacting southeastern England during the daytime. So I was really quite worried about just how bad the event could be. In the event, it probably wasn't quite as bad as some solutions suggested. So a little bit of a near miss in some senses, but yeah, it had potential to be a really quite major windstorm in the end. There'll be a special issue of the Royal Met Soc magazine or journal Weather later on this year with a number of papers about Kieran. It was really quite a major weather event for some parts of the UK with quite spectacular convective impacts over the Channel Islands, for example. Okay, moving on then to some of the other tools that we use then. This is going to be a little bit of a whistle-stop tour because I'm aware, it's 20 to 1 UK time. So Improver is the Met Office's probabilistic post-processing system, which Rob mentioned just there, which produces, well, it's a number of things actually. It produces a number of tools to help operational meteorologists, but it also produces the automated forecasts that will end up feeding into our app and our website. Outputs include percentiles and products with neighborhood processing applied, as well as some more traditional probabilistic outputs. There's a paper in BAMS last year by Roberts et al, which explains a lot more about how Improver works. Just want to show you an example of one or two products from Improver. This is taken from earlier this month from Storm Pierrick. So I was on shift during this event, and basically Pierrick's this one here, named by Météo France, and it moved then sort of east-northeastwards across the UK with a swathe of high winds on its southwestern flank. And also the rate of translation of the storm meant that we had some really quite prolonged rainfall on the northern flank of Pierrick over parts of Scotland and northern England. So you can see this is midnight on the 9th of April, and here's a radar and a satellite radar image with thunderstorms over the Netherlands there and parts of France slightly earlier in the evening. But it's this swathe of rain lingering over parts of Scotland that allowed some very high rainfall totals to build up and became quite impactful. And the magnitude of wind on the southwestern flank of the storm was also a little bit of a concern. So we had a pair of medium impact warnings out for this storm, one for southwestern England and this is wind, and then a rainfall warning for a large part of Scotland. And if we just then look at some products from Improver, now the way we set Improver up, the color scheme here isn't great. So the red ring you can see here is basically circling where the UK is, just to try and help navigate you all. And then what we've got here is some probability maps. This one here is for the probability of 10 millimeters in the hour during any 1 hour period between 15Z on the 8th and 3Z on the 9th. So this is quite a novel product that allows us very quickly to assess over a more prolonged time period whether or not there's going to be some high hourly rainfall totals building up. So instead of having to work your way through 12 different frames to see if there's going to be 10 millimeters in the hour or whatever threshold you pick, actually this really zones into just seeing if that could happen in a longer period for 1 hour. So that's a really useful product. Here we've got a slightly more traditional product of the threat of 24 millimeters falling in the 24-hour period between during Monday and Tuesday of the storm. And you can see the shape of these squares is such that there's some neighborhood processing applied. You'd expect it if it was just raw model output, it wouldn't look quite so regular, these shapes. So this is neighborhood processing being applied, which allows the probabilities to be both a bit smoother and also account for some of the uncertainty that you wouldn't quite get from the size of the ensemble. So it's a really helpful way of basically understanding risk a bit more clearly. And then here we have a probability of wind speed exceeding 60 knots during the early evening of the 8th of April. And so what you can see that if you just bear in mind this slide of this image and this image, you can see this area of high winds that ties in quite nicely with the warning that you can see here. And then this swathe of high rainfall totals, well, part of that's captured over Scotland, where it had been very wet in the build up to this event over Scotland. So there was a lot of sensitivities around potential for high rainfall totals causing impacts there. So if we just look at how the event manifests itself, then this is 50 millimeters of rain in Improver in 24 hours. And this is the verifying rainfall totals. This is taken from a private website, Roost Weather. And what you can see here is that where the 50 mils or more fell in 24 hours actually was captured quite well within Improver. You can see verifying. You can see parts of northwestern Wales picked out, the Isle of Man here picked out, and then also a large swathe of the far north of England and southern Scotland. So I think in this sense, Improver did a really good job and provided us a really useful steer with some good information. And this demonstrates both the value of an ensemble approach as well, because individual runs of UKV wouldn't have quite given us quite the same information. So yeah, it's provided a really nice steer from the ensembles. And then looking at wind, what we have here is the wind reading from the Scilly Isles. This is St Mary's Airport. So the Scilly Isles are the very small cluster of islands just to the southwest of mainland UK. And you can see what you want to look at here is the blue, and you can see that in the evening we had gusts getting up to 60 knots or so. And yeah, that ties in quite nicely with this narrow swathe of high winds picked out in Improver. So hopefully that gives a little bit of a sense of the sorts of things that Improver could do. It's a really, really useful tool and a really nice way of presenting ensemble information with, as I say, some traditional bits, some traditional diagnostics and some more novel diagnostics as well. Now, moving on to a couple of hazard impact models that we've made. We've been developing some hazard impact models to help us understand and forecast specific hazards. This one's called the Surface Water Flooding Hazard Impact Model. And what it does is it applies high resolution convection permitting ensemble data to hydrological models and an impact library based on rainfall return periods for different event durations to present the risk of surface water flooding on UK county scales or grid box scales. So you've got a number of different inputs. You've got the meteorological model. So in this case, MOGREPS UK. You have the hydrological model, which is called grid to grid, which tells you something about what sort of runoffs could happen from river responses. The impact library is basically a history of where there's been impacts from rainfall events and how much rain fell to cause those kind of impacts. Putting them all together then gives us an indication of whether there could be impacts from an event, and if there are going to be impacts from an event, which is the most likely impact column for them to fall into. So in NUSWAS, we talk about high, medium, and low, and very low. This is actually, it's designed aimed more at the hydrometeorological community, and they use a slightly different impact matrix, which is why it says minimal, minor, significant, severe, but it's the same kind of thing. There's more information about it in this Aldridge et al. Paper a few years ago, but basically this is quite a useful tool to try and understand how an event may give impacts, and taking the probabilistic element of the ensembles then allows us to understand something about the likelihood as well. So yeah, this is a pretty useful tool. The vehicle overturning model is also a pretty useful tool. This is something that relates the probability of wind gusts from MOGREPS UK exceeding known thresholds where vehicles can overturn to describe vulnerability. And we also have things like road orientation and altitude built into it. So what we have here is we have a map of the UK road network, or these are the main roads and motorways, and you can see that this slide is taken from the time this chart is drawn. And so you can see what it's flagging up here are areas where the yellow is where there's a heightened risk of vehicle overturning from winds being perpendicular to the road network and blowing over, in particular, high-sided vehicles. This Hemingway and Robbins paper tells you more information about that. We also have a Stingjet proxy tool, which is something that I worked on. This is based on the premise that CSI, so conditional symmetric instability, is present in storms of Stingjets. The presence of D-scape in the right part of the storm, so in the sort of southern quadrant of the sort of southern half of the storm, that's a proven proxy for Stingjet activity, and we need a proxy because CSI isn't really captured in coarser resolution models. And then using the MOGREPS G ensemble, what we're doing here is we're testing for the presence of D-scape, applying a filter to ensure that D-scape is being released in a moist environment in the frontal fracture region. So you can see here from this schematic, you can see where the frontal fracture region is, so down here. And what we found with this diagnostic, it produces output like this, which gives you a bit of an idea of the numbers of the different numbers of the MOGREPS individual members, and then the circles represent where there's potential for D-scape to be released. And what we found with this is it can give you a good indication of whether a Stingjet could occur or not, certainly in model space. And even if a Stingjet doesn't occur, actually what we found is that this tool is actually a good discriminator between low and medium and high impact windstorms. So it's actually a pretty powerful and pretty useful tool, and allows us to advance our thinking about Stingjets from a very crude conceptual level of just needing to have a Shapiro-Kaiser type evolution to thinking about it a bit more holistically and considering the broader continuum of when these kind of when a Stingjet could occur. So now moving on to, there's only a few more slides to go, and just moving on to one or two other things. Here we've got some examples of what some high impact events looks like. What you find is that some high impact events are also quite memorable events. We're in the high impact column, as you saw with Storm Kieran there, but we also have, this is the beast from the east. This is Storm Emma. Some of you will know it as. This is in the UK it's known as the beast from the east, in early March 2018, where there was some really quite spectacular amounts of snow affecting some parts of the UK, in particular eastern and southern UK, where I live on the south coast of England. There was a good 24 hours of really quite solid snow, and it's the most snow I've seen in this area since I've lived here. Really quite spectacular snow on the beach, yeah, it may well be a one-in-a-lifetime event really for me, really. But that was a pretty spectacular high-impact event with a multitude of warnings out. All these warnings you can see here were the range of warnings that were in force for the beast from the east in the 2 or 3 days that it lasted. This warning here is the extreme heat warning that we pushed out in mid-July 2022 when the UK exceeded its record temperatures. I think 40.3 was the record temperature we had in the end. And then this one here is Storm Eunice, which is a pretty memorable storm and one of the series of storms that Rob showed in his talk there, and you can see the gauntlet of warnings in force for that storm. So hopefully it gives you a bit of a flavour in a sort of more typical meteorological chart sense of what some high impact events look like. Storm naming is something that we've been doing for the last few years, and this is really important, really, to help communicate the message around high impact or higher impact events. It's a really nice collaboration and great to be working with Economy and Met Éireann on this. Storms are named when a weather system has or is likely to lead to an amber or red warning. That's when we would name a storm. The criteria is slightly different for Met Éireann and Economy. Naming, as I said earlier, is mainly to do with wind, but rain or snow impacts can be taken into account so long as wind will also be impactful as well. What we don't do in the UK is that if a storm's already been named by another storm naming collaboration, we wouldn't rename it. Ex-tropical cyclones wouldn't, if they were going to be impactful over the UK, they wouldn't get a new name so as not to confuse things. Now, the next few slides then concern a climatology of NUSWA's warnings. So what I've done is I've looked back through the last 10 to 12 years of NUSWA's warnings to get a bit of a sense of how many warnings we tend to get per year, that sort of thing, to build up a bit of a climatology, if you like. So we get typically there's about 400 to 500 NUSWA's warnings issued a year. In quieter years, such as 2017, we would issue far fewer warnings. 300 to 350 is typical in quieter years, and 600 to 700 is quite typical in particularly bad years. 2012 was a really bad year for severe weather. There was a lot of severe winter weather and also a lot of severe summer weather. Last year was actually quite a heavy year for weather as well. We had a lot of warnings, particularly during the autumn when we had a lot of wind and rain events affecting the UK, but also there was 1 or 2 other parts of the year that were quite busy weather-wise over the UK. I dare say it would have been the same for the Netherlands, Belgium and Ireland as well. So this graph here, or these graphs here, then show focus on amber and red warnings, and what you can see is this helps perhaps highlight some of the more severe years. So 2018 and 2012 were pretty severe years. A lot of the warnings in 2012, a lot of the amber and red warnings were tied to winter weather. 2012 we had severe weather through the whole year from what I remember. There was a lot of wintertime storms between 2014 and 2016. There was a lot of flooding in the UK, and that accounts for quite a lot of warnings then. Bit of a quieter period 2019 and also 2021, 22, and then a lot more active last year. Looking across when these amber and red warnings are issued through the course of the year, what we find is that there's, as you would expect, a bit of a peak in winter, so the most severe weather tending to come in the winter. But there is a secondary peak in July in particular, and that reflects summertime thunderstorms and heat warnings. April, May and September are the months with the fewest warnings, as you can see here, particularly April and May. In terms of what elements make up the largest percentage of warnings then, well, rain is by far and away the largest percentage of our warning. Rain gives us our most impacts in the UK. For a country that's quite used to getting rain, we do tend to get quite a lot of impactful rain events. So close to 40% of our NUSWA's warnings have been for rain. Wind, snow and ice then follow as the next most frequent categories of warnings that we issue. Thunder and fog, then not quite so frequently, and lightning and heat, we don't issue too many of those warnings. In terms of where warnings sit by impact, so what you can see here is this categorizes the different warning categories by impact. So if you take all the warnings together, you can see that about 60% of warnings are low impact and less than 5% for high impact. But what you can see is that with fog and ice, most of those warnings are for low impact warnings, whereas when it comes to thunderstorms, actually medium impact warnings tend to be the most frequent impact level that we associate with thunderstorm warnings, which is logical because they obviously can be pretty impactful events, with flooding tending to be the main impact from that. And then, yeah, with rain and wind events, they tend to give you slightly more medium impact events than average. So yeah, most of our warnings are low impact. We have relatively few high impact warnings. Fog and ice tend to be lower impact. Thunderstorms, and to a lesser extent wind, snow and rain, are more likely to be of a higher impact, demonstrating their greater potential societal impact. Areas in the UK we warn for most are in southern and central Scotland and northern England, and then Northern Ireland, Shetland and Orkney, and the eastern side of England and Scotland are the areas where we warn for least frequently. And then, yeah, this is my final slide then. So we have a team of people called the Met Office Civil Contingency Advisors, MOAPs we call them for short. So this is a team of about 25 to 30 people. They're distributed across the UK, and what they do is they engage with emergency responders, multi-agency resilience groups, and local government and central government to understand how severe weather will impact different regions and communicate the warnings. So they're a really, really critical cog in the NSWAS process, because they're both communicating the warnings and providing us situational awareness regarding what potential impacts could be. Outside of severe weather, they build relationships with the responders, help assess weather-related risks, and develop severe weather plans. And this involves embedding themselves with what we call local resilience forums. In all the areas of the UK, you have these local resilience forums where people drawn from different sectors of society that have an interest in severe weather will come together to help work together and understand what the impacts of weather events can be, and then work to mitigate against the impacts during events. In the build up to and during severe weather events, the MOACs will feed situational awareness of the potential impacts back to the expert weather hub. They'll communicate the expected weather and impacts as well. And this involves a lot of multi-agency teleconferences and meetings where they provide specialist meteorological advice. As well as working resilience groups, the team then engage with the devolved administrations. So that's the government in Scotland, Wales and Northern Ireland, and also local and central government. And yeah, as I say, this team is absolutely essential to the communication and forecast. And in fact, many members of this team have been operational meteorologists. So that was my final slide. We've got a little bit of time left where we can take some questions, but I'm aware that I talk quite fast, and so some of these details might have gone a little bit too fast. So if you do have questions, I'm also happy for you to contact me by email, and I can answer things more clearly and in slightly slower time. I'll also post a list of links into the chat as well, that will help provide a bit more background to some of the things I've probably gone through quite quickly, and also the papers that are cited there in the presentation. There's links to that as well, including one that, well, I think Rob's involved in quite a few of the papers actually that are cited there, but there's definitely one about EPSW there as well. So yeah, with that, are there any questions? Oh, right, okay. Yeah, that's a good question. So yes, the warning count is a very, very simple warning count, Graham. It is basically every warning that we've issued. So that would include updates to warnings, and that would include a change from yellow to amber. So a change from yellow to amber wouldn't be the same warning. That would be a new warning. Every single warning that's issued, I'm just taking as a new warning. So yeah, it's very simple. So yes, so just looking at Alexandra's question then from Geosphere in Austria. So the way we do our warnings, Alexandra, is that ideally we would use visual weather, seeing as though that's one of our main tools. But the way we do it at the moment is we have a standalone module that's web-based that we use to draw our warning polygons in. That introduces a slight inefficiency in that in that we haven't got the meteorological data in the same module, but it's for technological reasons of being able to send the warnings out. And I'm sure that a later generation, or next time we re-update this tool, I'm sure that will do something perhaps a bit more integrated into visual weather, or allow us to have layers of meteorological data within that. But yeah, it's a standalone separate tool, Alexander. And if you want to find out a bit more about it, or want me to show you it, we can have a Teams chat about that sometime. So just drop me an email. Okay. And then one from Salford. So yeah, the MOAC team is part of the Met Office Salford, and they then liaise with a number of other organisations. So that's how we find out some of their concerns and interests. And then Hassan, can you tell us a little bit about how you have defined the impact matrix with your stakeholders? So the way that worked was we had a series of meetings around the UK, in different regions of the UK about 10 years ago, where people from different different parts of the emergency responder community and government came together, and we went through some exercises where we talked about different weather events and discussed what would happen from those weather events, what kind of impacts those weather events might be expected to generate, flooding, travel delays, this kind of thing. And then we asked the people attending whether they saw this as high, low, or medium impact. So we built up a sort of consensus as to what type of impacts constitute low, medium, or high, and that was a consensus involving meteorologists and involving other people with an interest in severe weather and impacts.
One question in there I don't think we've answered, asking, do we use visual weather to manually define the warnings and polygon areas, or is there another tool we use? I think that we use the warnings hazard manager, don't we, to define and issue warnings?
Yeah, sorry, I thought I'd answered that, Rob. Sorry.
Oh, sorry, maybe you did. I missed that.
No, sorry. We have a standalone web-based tool to do that, Rob, called Warnings Manager, as you rightly say. And Alexander, I'm happy to give you a demonstration of that if you get in touch with me, and we can organise something.
Cool. Well, thanks for inviting us along. It's good to have the opportunity.
Yeah, definitely. Yeah, it was good. Enjoyed that.
Yeah, it's really good.